RBCDSAI series. Professor Sunandan today, who is visiting Chennai on a very odd day. We had some trouble in figuring out how to plan his day today because of the events that are happening in the city. But just to sort of introduce him, he's an assistant professor in data science at Indiana University School of Informatics and Computing. And something which I'm sort of interested in is that he's working on data science for social good, and probably we'll have some time later or tomorrow maybe to discuss about some of the programs that we run here at RBCDSAI with him. And what he does essentially is to build computation models that leverage the data and apply them to a broad spectrum of problems of social and environmental sciences, agriculture and health and other fields. So sort of very much overlaps with some of the interests that RBCDSAI has on the area of social good. He uses new social media, time series, etc., applies standard all sorts of different data science techniques and AI/ML techniques to lead to solutions that can be derived from these social data. Before this, he did his postdoc. Before Indiana, he did his postdoc with Jennifer at Moore-Sloan as a Moore-Sloan postdoctoral researcher at NYU Center for Data Science, where his research actually was an award-winning research that explored problems of illegal online wildlife trading utilizing complex digital text analysis. And prior to that, he has done his PhD with Dr. Lakshmi Narayanan Subramanian at Current Institute for Mathematical Sciences at NYU. So it's a pleasure to welcome him again, and we look forward to your talk. Thank you.
Thank you so much for that wonderful introduction. So good afternoon, everyone. Thanks for coming. It's kind of a pleasure that my visit to this wonderful city coincided with the visit of our Prime Minister. So that's something I'll remember from this trip. Let me try to open the slides. There you go. So today I'll be before. So before I start, let me give you a vision of my research. So you see a lot of different types of data available online, from online news, social media, scholarly articles, like research articles, which we publish and which are all available online, and a good amount of them are actually like freely available. And then you have e-commerce data, online educational materials, and online reports. So my research focus is to use this diverse set of data sets available online, mostly text, and build like novel machine learning and NLP models so that we can address a bunch of different types of problems. And I focus on two problems to have one of the two impacts, either a social impact or economic impact. So all my past and present works actually has this focus. So in today's talk, I'll be focusing on a combination of them, how we can use online articles, like research articles, scholarly articles, to extract information that can solve a very important health problem. So what is Sjögren's syndrome? So Sjögren's syndrome is a very rare autoimmune condition where your own immune system, your immunity starts to attack healthy cells. In this case, it attacks glands which produce tears and saliva. So patients who have Sjögren, they show symptoms like dry mouth and dry eyes, and sometimes you can have like joint pains. So what happens is when you are showing this kind of symptoms, with dry eyes, you will go to the eye doctor, the ophthalmologist. With dry mouth, you will go to and see a dentist. With joint pain, you will go and see a general or a rheumatologist. So they don't communicate with each other. So all these symptoms are not seen together. And it becomes very hard to diagnose because the dentist will treat dry mouth, completely ignorant that this patient is also showing symptoms of dry eyes, and that might lead to this disease. As a result, As a result, what happens is it takes a lot of time to diagnose this disease. And in the US, the current average time for diagnosis is 5 years. And by the time the patient's conditions deteriorate, so it's a big issue in the world of medicine. So why this is a problem? Like, we have so much information, we have electronic health records, we have these scholarly articles which are publishing research about this disease, but there has not been much focus on to address this problem. So no comprehensive knowledge base of factors or associated conditions which might help a diagnostician to diagnose this thing, this disease. Another thing is you have heard that dry eyes, dry mouth, they are very common symptoms and they're associated with a bunch of other diseases. So if you show the symptoms, the doctor will not readily think, okay, this is an early signal for Sjögren's syndrome. And as I said, like, patients record because they visit different specialties, the information is stored across different data sets, and they are not put together, which also becomes a problem to have a data mining approach for this issue. There is a solution. The solution is, there is an interest among researchers on this disease. So there's a lot of papers, a lot of research is done, a lot of papers are published, which perform observational studies on patients showing these symptoms or diagnosed with disease. And a lot of the important results are expressed in those articles using causal statements. When I say causal statements, I mean that sentences which have an information about causality, like renal tubular acidosis is a common cause of hypokalemia. So which says that one event is causing another event. So if you can extract this kind of sentences and extract the corresponding causal event and the effect event, so we can say that this is a causal event and that's the effect event. So we can So somewhat solve this problem of lack of information, lack of a knowledge base using this approach. But to be very honest, like as far as my research is concerned, so I was not looking into solving this problem and thought, okay, causal sentence extract. I think I'm back. Okay, thank you. Sorry about that. So yeah, I was working on how to extract causal sentences from text or causal information from text. And then I thought, okay, this is a good place where this idea can have useful results. But why did I come to think of solving this problem? So let me turn the clock backwards for a while and say like how I came up with this idea while working on some of my past projects. So it all started with this diagram, this time series, which is nothing but the volatility in onion price in India, starting from 2013 till all the way to 2021. And you have seen like crazy stories over here, like in middle of 2013, we have seen a 50% rise in the price in just 3 weeks. And sorry, in 6 weeks. And 2 years later, around the same time, 75% increase in 3 weeks. And you might think, okay, it's happening in July, so maybe it's seasonal, monsoon is coming, maybe that has an effect. But you can, if you look at this plot carefully, you will see that things are happening in January, things are happening like in end of a year, November, December. So it's not seasonal. But onion is a very important product, the food product in our culture, right? So we put onions, most of us put onions in all our cooking, all our dishes. And so the impact of onion is onion price, or like soaring onion price can have a catastrophic effect. And we have seen in the past that this has become an election issue and has led to the anti-incumbency factor, which led to the fall of the ruling government. And there are other kinds of impact, like this report is saying that crime rate can increase because of high onion prices. But the good news is we get information why. So if you want to answer this question, like why onion price is rising abruptly without any patterns, we get signal from the news. So if you browse news, you will see that there is a good coverage, not only about onion prices, generally about food prices, a lot of coverage. And we see some of the reasons in those news articles, like weather, like too little rainfall, sometimes too much rainfall. And there can be issues with transportation, like transporters striking or costs going up. All these factors lead to the sudden increase in price. And sometimes government policies, the government suddenly decides to ban export or ban import. Sometimes to mitigate the effect, sometimes a decision might lead to this issue. So then the question here becomes, how can we efficiently mine events from news articles? So mine this kind of information from news articles and use that as features to predict prices. And so our focus became to address that problem. So what we found out that events from news articles are mostly described by certain types of words or verbs called event triggers. So like Joe Biden is elected. So elected is the event trigger, which kind of tells you what has happened. Or for example, a Texas A&M cadet killed in crash. So killed, that's the event trigger. A word which is describing the event, which is telling you what has happened. You might know, just listening to the word killed, you might not know who was killed, how he was killed or she was killed, but what you know that what has actually happened. So if we can identify event triggers, we might be able to mine these events efficiently. So now let us look at the anatomy of a news article. So here you see that usually in news articles, the title has this event trigger, which is a description of the main story of the news article. In addition to that, you have other event triggers. Okay, so main event trigger is telling you that this story is about protest. Farmers are protesting. That's the main story. Why they are protesting? Because the construction of an expressway, which I think is taking up their farmland. That's why they are protesting. So construction is a subsidiary event. Protest is the main event. The main event protest is associated with this subsidiary event construction. Then, as I said, like when I heard killed, I know what has happened, or when I heard elected, I know what has happened, but who was elected, where was elected, what was the election about? All these things are missing. So to complete the story, so event triggers are giving you a generic information. To complete the story, you need to have other information like location, time, and topics. So our event model, which is based on this idea, is about drawing event classes. So event classes are broad description of events, like protest is an event class. And this news, particular news, specific news is drawn from the event class protest, but it is the whole story is completed by looking into the location, parties involved, the topic, and the time. That completes this whole story. So after we learned these event classes, so our assumption is that each event class can be represented using event triggers. Synonymous event triggers will form one class. Like for example, you see that protest. So protest is an event class which is described by event triggers, synonymous event triggers such as demonstrate, agitate, strike, etc. So this is what we would like to build. From a large news corpus, identify event classes and represent each event class using synonymous event triggers. So our assumption was that a corpus of news article is a complete description of event classes. So this world has a finite number of events, a type of event class, and a large news corpus spanning many years will be a good proxy to interpret that universal event class. Then we assume that every news article has only one main event. There can be other events, but there's only one main event. That's what the story is about. And this event is drawn from the generic event class. And an event, actual event that has happened, is an instance of drawn from that event class. And the story is completed by few other meta information like date, location, and topics. Like topic, when I say topic, I mean also like people involved, organization involved, and other things. So here's an example. So event class, accident is an event class. Then you have two events, which are instances. Like one event, Air France crash mid-Atlantic in 2009, and a train derailed in Spain in July 2030. So both these events on the right-hand side, they are drawn from this generic event class accidents. And what you see is these events being recorded in the news media as news article. So there will be news articles where these two stories are going to be the main event. So we produced this using like a probabilistic graphical model, a generative model. So what we see over here, this is observed, and this is what we want to infer. So this is a news article which has main event triggers and subsidiary event triggers. And this is the event class. So these boxes are event classes, and the red dots represent the synonymous event triggers. So if this is protest, this can be protest, this will be agitate, this will be strike, and so on. So we can observe this, but we need to infer this. But we assume that this is generated from this abstract class. So first, to generate a news article, first you sample a main event. So as I said, the news article has one main event. So you select one of these boxes. Once you select that, you select several event triggers from there to represent the main story, main event. Then you repeat the process for subsidiary events. But subsidiary events, we assume that like main event, there can be only one main event, but there can be several subsidiary events. So you need to sample more than one. Then the process is the same. So we trained this event model from a large news corpus of more than 10 years, which had like 700,000 articles and more than 600,000 unique words. So now what we can do with this event? So the original problem was to identify whether we can predict onion prices or food prices using events. So we built this thing called recurrent event network, which is like a sequential LSTM model. But instead of like what happens in a sequential model, like the current output is a function of current input and past input. So every state is a function of current input and the past output from the past state. And here we use the event information from the event class. So we have a finite event class. So we have 200 event classes. So we will represent this input using a vector of size 200. So every day, if this is modeling daily price, and we are trying to predict daily price at the end, next day's price. So every day, what was the value of a particular event on that day will be represented by the corresponding cell in that vector. So this whole idea is that tomorrow's onion price or other food prices will be a function of what was the price today or day before yesterday or day before yesterday, and what events happened on those days. Was there an election? Was there a transportation strike? So we are capturing this information to predict onion prices or generally food prices. So here's some results. So we applied this on like 10 or 11 different food items, but I'm just showing results for potato and onion because those are the two most consumed food products in India. And we see that compared to several baseline models, we compared our model with a non-linear sequential model without using events, which is RNN, or we use linear models and showed that we use two linear models, one which used events, one which did not use events. So ARIMA, which is a very well-known linear model for time series forecasting, we implemented an ERIMA or an event ARIMA to show that using event information for this kind of problems makes sense, has benefit. And if you look at the results, you will see, I don't know whether the numbers are clearly visible, you will see that REN, recurrent event network, the RMSE value is way less than the RNN. So if you add events, it is giving you some benefits, event information for predicting food prices. Similarly, compared to ARIMA, ERIMA is producing less error. So this is to demonstrate that using events in this kind of problems has its benefits. So we have also used this to predict cryptocurrency values, and we see very good results, and also for stock prices. For stock prices, we observe something funny. It cannot predict like a very large value of certain company stocks like Amazon, Google, which did really well in the last few years. Their stock prices soared. Though our model can predict the trend, but it cannot predict the actual value because it's so higher than what was expected. So beyond this, apart from prediction, we also wanted to learn like what are the events which is actually making one observed rise happen. Like if I see suddenly like the next 3 weeks, onion prices are soaring, can I understand like which events were actually responsible? I know a bunch of events which are responsible, but for this particular case, which events were responsible? So we did this using likelihood ratio test to understand which events were generally responsible for onion price rise. We saw that it can be strikes, it can be government policies, it can be festivals like during Diwali, during the time like October, November, there's so many festivals happening, prices go up. But this is not scalable because we used all the events and ran pairwise likelihood test for all, and we had around like 300 events. So it's not scalable. So what can we do? So we observed something that if we draw time series of words and compute the correlation, we see something very interesting. Like the correlation of the frequency of the word malaria goes up 2 months after the frequency of the word monsoon or flood go up in the news media. So we see a spike in monsoon or flood, the spike of frequency of these words. 2 months later, we see the spike going up for the word malaria. So does that mean that malaria or flood is monsoon or malaria flood is causing malaria? Well, there is a way to figure that out. So we can compare time series, and if you see correlation, but it has a unidirectional time lag. So suppose this is monsoon and this is malaria. This is like representative data. This is not actual time series. And if you see that there is always a constant time lag between the spikes of these two time series, using this Granger causality test, we can infer whether this is causing this. So we use this idea and created this causal network of unigrams and biograms from the news media. And so this is a excuse me. This is a snapshot of that network. And then we used so we call this word causal graph, and we extended this idea to create something called predictive causal graph, and see, instead of using associative features, which is traditionally used in machine learning, can we use causal features? And we showed that based using the same data, Google News corpus and New York Times corpus, using the same stock price data, we are performing much better. So we had 3 versions of the predictive causal graph using just unigrams or words, bigrams, and using both, which is performed way better than an existing work which use the same data on the to predict stock prices. And not only that, we actually can explain some of the factors. Like when we are trying to predict the stock price of Apple, we see this word music, which kind of is counterintuitive. But then you see reports like this, or articles like this that music has an important role to play behind Apple's success. That's why music became a causal factor to predict Apple's stock price. So this was how I was getting into causality and how we can use causality for prediction. Then again, a little inspection revealed that if you go into the text of those articles, instead of looking into like more abstract level, you get much more information. Like this story, which is again talking about food price rise. If you read the sentences, you can get much more information, which is very easy, very natural for us humans, but may not be that straightforward for machines. So we can learn about why prices are rising, what is coming next, are we expecting a drop or rise in the price, and what are the events that might lead to a change in the future. So again, can this help us with better prediction? And the crux of this problem is we see a lot of why questions, why prices are rising, like not why questions, answer to why questions. So that means that maybe extracting causal relationships from the text data can be helpful. So causality is a very important concept in many different domains. And we have seen that like in medicine, in economics, in social sciences, researchers perform very elaborate studies, experiments like randomized controlled trials or observational studies to infer causality between specific events. Will this drug reduce the effect of a disease? Like a year-long or tests, studies which span several years are conducted. And what happens if it's successful? If the results are published in research articles. So we will, in those research articles, we will see statements which is saying this causes that in some way, not exactly A causes B, but we can say A leads to B. We have seen that A is likely to cause B, something like that. So the problem over here is identify such sentences like them over here and identify three kinds of information. What is the causal entity over here, causing effect, the causing event? What is the effect event? What is the effect event? And which can be done by identifying the connector or the relationship. Like causal information is encoded by specific verbs, specific words. So if we can identify them, we should be able to identify sentences which have this kind of information. Then the third step would be to identify these two different entities. But there are many challenges, like natural languages, like English. You can say the same thing using 15 different ways or 20 different ways. And causality is no exception. So you have very straightforward marked causality. So causality can be marked or unmarked. And in marked, you can have explicit causality, where you have this kind of words like causes, leads to, results in, straightforward, very pointed, which will tell you, okay, this sentence has causal information. But then you can have other words which can be used in both causal and non-causal context. For example, as, like in this example, as is used in the causal context, that because the issue was resolved, that was a causing effect, the causing event, the effect was, there was no debate. But you can see that as a word, as a connector, is used more number of times in a non-causal context. So just looking at the word as cannot be good enough. And then you have unmarked. Look at this sentence. We as humans can understand that the heat stroke is what is causing this heat strokes. It is the rising temperature. But linguistically speaking, this information is not encoded because there are no causal markers in this sentence. Then you have multiple cause effect pair, that one cause is leading to another one effect, and that effect is becoming a causal factor for another effect. So you have cascading or transitive relationship. Then you have multiple relationship like tree-like structure, like one causal causing event can generate into multiple effects, or one effect is generated by two causal factors simultaneously or independently. And then you can have multiple independent pairs of causality in one sentence. Finally, linguistically speaking, grammatically speaking, you might not see the same structure. Like in this sentence, the illness caused by deficiency of vitamin D is called scurvy. You might think, okay, what is causing, what results into the deficiency of vitamin D? You might think it's illness, but actually it's scurvy. So you might have very irregular patterns. So to solve this problem, we used this standard data set, two data sets called SemiVal 2010, which has a lot of tasks, including identifying causal relationships. And then there's another data set called ADE, or Adverse Drug Effects, which is a data set which has only one type of sentence, which kind of explains drugs and their effects, which are also causal in nature. So these are fairly small data sets. You can see in this era of big data, we don't deal with data sets which has 1,000 or 3,000 sentences. So we try to create our own. We are not yet done because we are still annotating, but we have collected 18,000 sentences from scholarly articles, research article abstracts, freely available in the PubMed database. And these 18,000 sentences are all about Sjögren's syndrome. So I'll come to that data set a little later. So we implemented a reinforcement learning based model. So the reinforcement learning, the setup is there is an agent which is trying to traverse in an environment and is doing that by moving from one state to another, and is doing that based on taking some action. So I'm in one state, I'll take this action out of many actions possible, and I'll move to the next state. In the process, what I'm trying to do is, as an agent, trying to maximize the reward. So I will take an action, go to another state. If I see that, that will help me to get a positive reinforcement in terms of higher reward. So how we can apply this in this context? So agent is a neural network, which is moving from one state to another, So agent is a network which is moving from one state to another, and states are basically the tags. So we have 3 or 4 different types of tags which can be used to represent a word for this problem. One is C, which means causal, like this word is causal in this context. Other word is E, which represents the effect. Then you have hybrid for transitive relationships, which is effect in one case, cause in another case. So instead of representing them using 2 different tags, we create a new tag. And then you have N, which means that this word has no contribution in the current causal relationship. So for this sentence, Sjögren's syndrome can cause corneal perforation and also mucosal perforation, which may eventually lead to, surprise, surprise, lacrimal fistula. Not very interesting. You have, if you look carefully, this has 3 causal relationships. Sjögren's syndrome is causing 2 events: corneal perforation and mucosal perforation. And mucosal perforation in turn is causing this lacrimal fistula. So you see 4 different types of tags in this case. And the agent's task is to move from one state to another and trying to correctly predict the tag of that particular word. So this is the correct output sequence of tags for this sentence. And this is the state transition diagram of the agent. So agent, correct state transition diagram to produce this correct output sequence. Moving from first, it landed on C. Then in the next state, it moved again to C. That's a correct action taken, which means it will get a positive reward. And reward, the way we have defined reward, is that mu t represents the accuracy score at time t, current time. And what was the accuracy score, prediction accuracy at time t minus 1? So difference of that, which means that if I do something which will increase the accuracy, I am getting a positive reward. So as an agent, I'm learning that I should take that step. So in this case, moving from here to here for the first step is taking a step in the right direction, taking the right action. And you will see that it has correctly, if it's staying in the same state, it is correctly predicting the tag for the next word, it will get a positive reinforcement. So we use this active critic algorithm to implement this learning method, so that there are two entities, the actor, which is doing all this, and there's a critic who is giving feedback or putting a positive reinforcement onto the actor or the agent to do something good. And we also had some assumption that all cause and effect or hybrid words and phrases, they are noun phrases. So we will not consider any word or phrase which is outside noun phrases to be a candidate for causal, effect, or hybrid phrases. And one more thing is the job is not done yet, because you can see that it's not like POS tagging or named entity recognition like other NLP tasks. You cannot just produce an output sequence. You have to identify the individual relationships, multiple relationships, if there are any. So after this output sequence is generated, you have to parse the output sequence to actually identify the individual relationships. So here's a summary of the results. So we applied this onto two data sets, as I said, ADE, adverse drug effect, and the same-eval 2010 data set. And we see that we used a bunch of baseline models, like we used LSTM and BioLSTM using different types of word embeddings, like word-to-word glove, and we are only showing the top performing baseline models over here. And also we used a BERT-based model. We used the BERT representation, the contextual word embedding for this task. And we see that marginally our model is doing better. And then we looked into the literature and found all other works which have produced or report the top performance on these two data sets independently, like Lee et al., which they used BioLSTM, which was passed on to a CRF, a conditional random field, and Wong, the next work, they used attention mechanism, but not using LSTM, but CNN. And this work used Elmo and BERT on top of a bidirectional GRU-based sequence. So still, this guy is the best performing model, but we are not way behind. We are marginally, our results were marginally poorer than this best performing model. But for AD data set, we actually did better than the next best model by Zhao et al., where they used joint learning of entity and relationship. So this was direct evaluation. We also did an indirect evaluation to see how this can help in other NLP applications, like, for example, question answering. So we identified a few causal sentences, like studies show obesity may lead to memory impairment, and framed questions, causal questions. And if you are able to identify the cause and effect correctly, you should be able to answer that. So we had a set of correct causal questions with answers, like what obesity causes. It causes memory impairment. So we have a combination of questions to model this, to map this relationship. At the same time, we have negative examples, like studies in obesity. What studies can cause obesity, which is not true. So we have that two different combinations, and to see, to add negative examples to the set. So a question answering model should give high score to the first example and a low score to the next example. And what we see that using this approach, our model can identify correct pairs of cause and effect pairs with a precision of more than 0.9. And then we used a standard data set for question answering from Yahoo Answers, and only identified those questions which were causal in nature. And we found around 1,000 sentences. And what we found that it can correctly identify the causal phrase with a precision of 0.864. And when it can identify the causal phrase correctly, its performance in predicting the corresponding effect phrase is more than 95%. So overall, we see that like our method of using reinforcement learning to identify multiple relationships. Or one more thing, like the existing works I showed, they cannot identify multiple relationships. They only assume that there's only one relationship in a sentence. So we have better precision and recall, and we show good performance on other applications. So now the stage is set to see how we can now apply this model into the problem we want, problem in hand, that addressing the issues doctors, diagnosticians face in treating or diagnosing Sjögren's syndrome. So we saw this slide, then we took diversion. So we have causal sentences which can be helpful in certain ways. But before that, let's look at the long-term goals, the bigger picture here. So what health informaticians want to do is combine 3 different types of data: scholarly articles, which is pure text, and electronic dental and health records. As I said, like for Sjögren's syndromes, patient records are distributed across dental records as well as health records. And so if you can identify symptoms, like maybe the dental record for that patient said dry mouth, the health record for the patient said dry eyes. When you can combine that, that is a signal that, okay, this patient might have Sjögren's syndrome. So we need to merge that. And what are those factors? Dry out, dry mouth, we know about that, but there are plenty others which we don't about. Maybe some researcher, some group researched on that like 10 years ago, published 2 or 3 papers, and then it was forgotten, and it is lost in under a heap of other research articles. So that unknown factors, or not unknown because they are published, little known factors, little used factors can be mined from the medical articles. So my focus here is to identify certain factors. And in this case, the factors are, there are 4 types of factors: signs and symptoms, 4 types of factors which will describe Sjögren's syndrome or the conditions of Sjögren's syndrome. Signs and symptoms, associated conditions, risk factors, and diagnostic tests. And my job is to focus only into this part right now and not considering the other 2 data sets. But the problem is, like, identifying this kind of labels is not very hard. If you have a large annotated data set, it should not be very hard to do that. But what is holding us? Because annotation is hard. You need to have a person who has experience, knowledge on Sjögren's syndrome to actually annotate these sentences, taken from the research articles. And we have tried that. People get confused, and we had 2, like, not novices, but again, not experts. And when they tried to annotate these sentences using these 4 labels, the agreement, inter-annotator agreement was really, really low. So you really need a lot of skills and expertise to annotate this, which is not an option right now. And what we have seen empirically, like if we take all these pre-trained models, pre-trained large language models, they also don't perform well in this case. Maybe because we don't have enough annotated data set to fine-tune those models. But careful observations see that these are some of the causal sentences we identified. And so this is causing something. Sjögren's syndrome is causing something. If you look into this, you will see, so this xerophthalmia and xerostomia, they are like medical terms for dry eye and dry mouth, respectively. So this kind of sentences are talking about signs and symptoms and associated conditions. So when we go back to this diagram, so we can see that we can use causal sentences to identify these 2 types of factors, maybe not the other 2 types. So we created this annotated data set, collected this data set from PubMed on Sjögren's syndrome, and we could only annotate a small amount of them because it's hard. It's very expensive to annotate these sentences. So we annotated them with all the 4 factors, and then we found out of this around 1,000 articles, 383 were actually causal. So that's the set we were going to be working with. So this is a very simple approach, like identify whether a sentence is causal or not. And if it's causal, apply the reinforcement learning model to identify the factors. And those factors will be those little known factors we are going after. And as we can only identify effects or causes, but we don't know whether that's a sign and symptom or an associated condition, we are removing those labels. So we will identify factors and we will assign a label, whether it's a sign and symptoms, sign and symptom, or an associated condition. We will do that later. So here's a snapshot of some of the sentences we found and correctly identified the cause and effect from these sentences. And we see, okay. I don't know how to remove that, but I can just. Anyway, that's not important. Yeah, so you see a lot of signs and symptoms here. And also you see the remaining are the ones are associated conditions. So we compared our performance with other pre-trained and other models which have been trained to do NER, named entity recognition, or entity recognition for medical text, biomedical text, like glove embeddings in CNN, BioBERT, BioBERT and Gram-CNN. And we see that our model of identify causal factors outperformed all of them. And there are some reasons, because all these models, they have shown, like BioBERT has shown that it can do much better than BERT itself. But they are trained on a larger data set, at least 5,000 sentences or 10,000 sentences. We don't have that. Maybe this is too resource poor scenario for these models to work well. And we also simplified the problem a little bit, because we are only we have only 383 causal sentences on which we could apply our model. So we applied these models on those sentences as well. We removed the other two labels because our model can only identify signs and symptoms and associated conditions. So we removed the other two models as well, other two labels as well. And again, as I said, we are not predicting the labels. We are only identifying them as factors. So if this baseline models just identified it correctly, but put the wrong label. So it identified signs and symptoms and said this is an associated factor, or correctly identified associated factors, but it called it a sign and symptom. We did not put any penalty on that. It could correctly identify a factor. That was what was treated as a correct output. And this is, so we combine the individual pairs of relationship into a larger causal network. As you expect, Sjögren syndrome is right at the center. And this shows a variety of effects Sjögren syndrome can lead to, or variety of factors which can lead to Sjögren syndrome. And we can also see some other subsidiary relationships which we were not directly looking after, but we still found them. So this work has some limitations. First of all, like to have a complete information, complete knowledge base, we need 4 types of factors to further research on this disease, on this issue. We can only identify 2 of them. And again, you can identify them, but we cannot label them. I cannot say, okay, this is the factor associated with Sjögren syndrome, but I cannot say whether it's a associated condition or a sign and symptom. So we have to work to classify those factors into these labels. And one assumption is that we only use sentences which has the word Sjögren syndrome in it. But there are many other sentences where this term is not mentioned, but also has relevant information. We have missed those. And another thing is a strong assumption that we can only identify signs and symptoms and associated conditions using causal sentences is not true. There are many other sentences, like this one. 2 years after presentation, the patient developed dyspnea, cough, and xerostomia. It is talking about symptoms, but not using causal sentence. That means that we have to figure out other means to identify this kind of factors. So mine other types of relationships. So the future direction has like 3 parts. One is how to move forward with this project, and how to, and on the other side, how to make causal inference using text more meaningful, more robust. So the first one is just about this specific to the Sjögren syndrome project, that how we can exploit other relationships to have a more coverage of the factors from extracted from this data set, the research articles. Then you have another future direction, which is solely about strengthening, making causality from causal inference from text more robust. Here we are trying to figure out how we can represent the strength of a causal relationship. And the middle one is a combination of both. That now we have information from text. Now, can we identify entities from EHR, ADR, electronic health record, and dental record, and do inter-dataset causality to actually have meaningful information in a meaningful knowledge base? So I'll just talk a little more about the final point. So here, what we are trying to do is like causal relationship is not binary. So can we identify the actual strength of the relationship? So figuring out a metric called causal distance. The causal distance will vary from -1 to +1. -1 means negatively causal, which means like if this happens, the effect will not happen. 1 means it will definitely happen. If A happens, B will definitely happen. 0 means no causal relationship. And we are trying to address this using linguistics, using NLP, using words like likely, definitely. So if I say A is likely to cause B, means the strength of the causality is much less compared to if I say A will definitely cause B. So we are trying to model that. So I would like to acknowledge National Science Foundation for partially supporting this work and the team involved in this project. So we have PhDs and other graduate students and undergraduate students from School of Informatics looking after the causal inference part. And we have a couple of people from the IU School of Dentistry who are interested in the Sjögren syndrome disease. And I would also like to thank my PhD advisor, Lakshmi Subramaniam, and Shrikant Jagabatullah, who was also in my thesis committee, and 2 of my fellow PhD students, Anant and Ashwin, who were involved with the first part of the project, the predictive causal graph and the event model. And so I shouldn't say that Shrikant and Lakshmi are my past collaborators, because we together have co-founded this company called Verai, which I'm sure you know what the meaning is. And we are trying to figure out like how we can develop shock resilient AI, that there are so many things which are leading to shocks, and that's creating a lot of monetary loss, health, physical loss, and health related loss. Can we predict and make decisions based on that? So the 2 broad spectrum of products we have is Index IQ, which is like, can we identify forecast shock using those ideas I presented to forecast food price data? And if we can do that, can we use that to make shock resilient decision? So with that, I'll end this talk. Thank you so much. I'm happy to take any questions. Yeah.
Have you considered the causal relationship across sentences, or it is only within the sentence?
Right now, within the sentence, but you're right. Like there are cases where you see causal sentences across sentences, causal relationships across sentences. We are working on that. That's definitely on the radar. Thanks.
Thank you for the interesting talk, sir. My question was that the source from which we are extracting the causal relation, what if that source itself contains misleading or spurious information?
Absolutely, yeah, very good point. So we are using, first of all, when you're training the model, you're using standardized data sets like ADE or semi-val. So you assume that they have true information. But when you are trying to apply them into real world noisy data, like we did in the case of Sjögren syndrome, we actually applied them on scholarly articles. So for scholarly articles, we kind of assume that it has been peer reviewed. So all this information has been verified, reviewed, modified accordingly. So we kind of think, okay, this information, underlying data is correct. But if we want to use this on news data, we run into the risk of that. So we have plans to mitigate that, like we would see how many different sources have this relationship is coming from. If we see that this relationship is coming from multiple sources, then maybe it's true. But there are issues with that. But we don't have a specific plan yet, but we are aware of this problem if we are using like user-generated content or news data, because we see fake information, misinformation has propagated into mainstream media. Thank you. I saw quite a few raised hands. Yeah.
Yeah.
Hello. Hi, Sunandan. Yeah, this is Manikandan here.
Hi. Hi.
Yeah, hi. I enjoyed your talk. I didn't know it was actually happening there, so otherwise I would have come there. So some misunderstanding. One question I had was in the SEM-eval task 8 dataset. So what is the text on which the models are tested on? You have, my understanding is that you have pairs of variables which will have this cause and effect relationship, and then some pairs which will not have the relations. And then to all the methods, is there a common corpus of text that is provided?
Oh, these data sets, as I said, like this has been like been there for a while, and they have like standard split of test and training and test subsets. Is that what you're asking, or you're?
Yes, I'm asking about the training and test subsets will be basically pairs of entities which will have either a causal relation or no causal relation, right?
Oh, no. So SEM-eval has a lot of things. So I'm specifically talking about task 8, which is about relationship extraction and causal relationship extraction. So there you have cause and effect present in the sentence.
Okay, and so there are single sentences and then cause and effect variables labeled on them.
Yes.
Okay. So these different models like BERT and other, and including your models, are applied on those single sentences.
Exactly. Yeah. These data sets are basically sentence data sets. You have sentence. Each item in that data set is a single sentence labeled with cause and effect.
Okay.
But the thing is, like, I don't remember exactly whether it's the SEM-eval or the ADE, where all the sentences has the word causes or some form of the word cause, like caused by, causes, caused, etc. So these are very easy data sets. So now we are actually developing our own data set as well as looking into other. So there is a last year a new paper came out which has produced data set called CauseNet, which has like, I don't know, more than 20,000 relationships. But again, they are based on pattern matching. It was created from Wikipedia using pattern matching, and they used very well-known causal connectors like cause leads to results into to produce that data set. So it becomes very easy for a model to identify those, and as a result, in a real-world data set, the recall will be really, really poor, because in practice, we as humans use many other constructs to represent causal sentences.
Understood. Yeah. Thanks.
Sir, I have a question.
Yeah.
Like the transition diagram which you showed, like you have made it, means on what basis you have made it?
Which one?
The transition diagram which you showed, which poses a penalty if it is showing, but there was one transition diagram.
Just let me know which slide you're talking about. Is it?
Before that. Sir.
Are you talking about the causal graph, the word causal graph?
No. No, sir. No, sir. There was one transition diagram, like where you have identified the entities, 4 labels, and with that you were made a transition diagram there.
Oh, okay.
Yes, sir,
One.
this, yes.
Yeah.
So like this diagram is made on like what basis you have made this diagram?
What do you mean by what basis? So this is showing the process. So the agent will come at set C over here, and then because Sjögren syndrome in this case is the causal factor. So this is how, this is a representative diagram, shows the correct state transition for the agent for this sentence.
Okay, for this particular sentence.
For this particular sentence, yeah. So if you see, these are the state transitions. So number one, C to C. Number two is C to N, C to N. Take a random one, 8, N to H, N to H, 8.
Yes, sir.
So this is specific to this sentence, yes. So the agent will produce different state transition, will have different state of transition for different sentences.
But in this, you have not considered the connectors, like by which these are connected, like
No, we did not, because of this. We don't want the model to think, okay, presence of a certain type of words will have causal meaning in it. Poor precision. Poor precision. Maybe. I don't have a correct answer to your question yet, but if there are some latent patterns, which as humans we cannot perceive, if the model can pick on that, yes. Yeah, and to do those kind of experiments, what we need to do is have more data. We cannot deal with like thousands and 3,000 of sentences. To have a pattern like for the Sjögren syndrome, yes, but it's small. It's if you consider causal sentences, it has only around 400, and we are like annotation is expensive. So now we are like using this model to create a little more annotated data where we see that. So annotation is expensive when you are doing it from scratch. But if I ask annotators to, okay, this is the output of a model, you correct it, then it's easier. So we are trying to grow our data set. Yes.
Thank you, Professor Sunandan. It's an excellent, informative, purposeful.
Thank you.
How much one would be missing if English is the only language? For example, obesity, fetal bucket in German. How much we will be missing it, informations? Thank you.
A lot. Yeah, that's a very good. So you are asking whether this work can be extended to other languages? Yeah, I agree with you. We have not focused on that yet. We don't have the necessary resources to like creating an English language data set is taking us so much time. So expanding that to other languages is going to be hard. And I really want to try this out on Indian languages. We are becoming like, many of our languages are becoming stronger on the internet. And I've heard of this Indian Indic data set, which is housed by this center. So I would like to, that's something I would like to see if we can do this kind of things with Indian languages. I would be very interested in that. And of course, like other very resource rich languages like French, German, Russian, German, Japanese, because a lot of research is also done in those languages. And we would probably miss out on a lot if we don't. And what I would like, if you think of like the historical documents, earlier people used to publish papers in Latin or German. And if you are doing something which is historic, it can be about epidemiology, like something people research about a virus or a vaccine or some physical model. Maybe it's still available only in German. So yes, you have a very good point, and we have that on our mind, but we don't have any immediate plans to address that. Thank you. Yeah.
The states in your RL setup, are they tags or they are sequence of tags?
The states are tags, but the state transition is the sequence.
What do you use as state representation?
As
opposed to like BERT and Glove that you've compared with?
How
do you represent your states, those tags so that the neural network understands.
It's like using precision and recall. So if a sentence like this sentence, whether my boundary for cause matches exactly with the true boundary, my boundary for effect matches exactly with the boundary of the true boundary. Okay, so it might so happen that my model found out this is the cause and this is the effect. So this is partially true. So unless I have exactly the same boundary, for in this case, let me just say the true relationships will be obesity to pathophysiology and obesity to memory impairment. So unless my model is exactly matching the true label, I'm not going to give this as a correct output. Same is true with other models. So I'm comparing the final output of the baseline models and our model. Does it answer your question?
What I'm asking is, what's the input to the neural network of the RL agent?
Input, are you talking about like input like the embedding
The
we are
tag
using?
is the state. So you have to represent, how do you represent the state as an embedding?
Are you talking about state or the word? Yeah, I think you're asking about the embedding of the word, right? Like input sentence.
Embedding of the tag.
The tag is a variable. Tag is a variable, so you can think of the output as as something like this. Softmax output with 4 possible values. C, H, E, M. But for the input word, like you can have any embedding. And we didn't see any effect of any embedding on the output performance. We tried with Glove, we tried with Word2Vec, we tried with non-contextual embeddings like BERT. Yes.
So the previous slide you showed for explicit and implicit connectors. So the unmarked line, the unmarked sentence.
Yeah, go on.
So the unmarked sentence we can paraphrase into the explicit marked sentence, right? Like we are having AI models for converting, paraphrasing the sentence to simple. We can make a model for paraphrasing it and then use that explicit sentence to get the information we require.
So when you say paraphrasing, like, are you sure that it will always produce a marker?
But we, okay, we can make a model convenient to our.
Yeah, that's a possibility. Yes.
Then we can easily, like, we can get explicit marked sentence, and our model can extract data from it.
Okay, yeah, like interesting idea. I have not thought of that. Interesting idea, but I'm a little skeptical whether how well this can be done.
Like we don't have a full accuracy, but some 70–60% of accuracy would work.
Okay, that sounds like an interesting
because
direction.
I'm just coming from the AI for BARAT conference.
Okay.
So they have used paraphrasing techniques for Indian languages. So they have some 60% or 70% accuracy. So English would be having a better accuracy, like 80 or 85.
Okay.
So we can use paraphrasing and then extract the data.
Okay, that sounds interesting. Like I'll look into this. Yeah.
Thank you.
Thank you.
Yeah, thanks, Sunandan, for this exciting talk. And I think a lot of different questions came and
Yes.
it's sort of your talk is coinciding with AI for Bharat that we are having right now, I think, and that sort of makes it interesting. So on behalf of RBC, this is a small
Thank you.
window for you.
Thank
And we will, I think,
Thank you so much.
so there's tea and snacks outside, so please you can have further discussions.
Yeah, of course, I would love that. Yeah. And thank you for coming. And one thing, like from the questions, what I heard, not only like questions clarifying what I said, but also like I got ideas of this new direction. So thank you very much for that. The questions were really, really interesting to me.